Imagine a thick-walled steel cylinder, right? Like roughly the length of a 5-story building, just laid completely flat on its side.
Yeah, that is massive.
Right. And now imagine that if a single hole drilled into that 15-meter stretch of steel is misaligned by, say, the thickness of a fingernail. Well, an entire nuclear containment system could ultimately fail.
It is wild to think about. It really completely flips our intuition about heavy industry.
Totally.
Because we naturally associate that massive scale, like the multi-ton steel and the factory cranes, with just, well, blunt force.
Right. Brute strength.
Exactly. But when you look at the pressure-bearing infrastructure that actually runs modern society, brute force is a massive liability. The margin for error is essentially zero.
Okay, let's unpack this. Welcome to another custom-tailored deep dive, diving into the stack of sources you provided for us today.
Glad to be here.
So our mission today is to understand a highly specialized, almost totally hidden titan of manufacturing, the CNC drum drilling machine.
It's a fascinating piece of tech.
We are going to explore how heavy industries manufacture the massive cylindrical pressure vessels that literally power our world. And, how this specific technology solved a physical geometry problem that used to take weeks of agonizing, dangerous manual labor.
Yeah, we rarely think about the invisible backbone of our infrastructure. Like when you turn on your heat, you aren't thinking about the arrays of heating surface tubes in power station boilers.
No, definitely not. Or like the complex internal geometries of petrochemical refineries.
Right. But understanding this specific CNC technology is fundamentally about understanding how we control extreme pressure and extreme energy safely.
So to really grasp the mechanical problem this machine solves, we have to establish the physical scale we were dealing with.
Oh, absolutely.
According to the sources you provided, these cylindrical drums range from 1.2 to 1.7 meters in diameter, and they stretch over 15 meters long.
That is basically a horizontal silo.
Exactly. And they need hundreds, sometimes like thousands of holes distributed across their circumference and down their entire axial length.
Think about the physics of just moving a piece of steel that large.
It's got to be a nightmare.
It really is. Under its own weight, a 15-meter hollow cylinder will experience structural deflection.
Which just means it sags in the middle, right?
Right, exactly. It literally bows under its own weight. So traditionally, processing just one of these drums took 1 to 2 entire weeks using old radial drills.
2 weeks for one drum.
Yeah, 1 to 2 entire weeks. Workers would have to map out the whole coordinates manually, marking the entire drum with center punches.
Yays. That's where the geometric nightmare really begins. I mean, imagine trying to draw a perfectly spaced, millimeter-accurate grid of dots all over a giant 2-ton rolling pin.
That's a great analogy.
But you have to keep picking it up and putting it down without ever losing your exact zero coordinate, because the radial drill simply doesn't have the reach to cover a 15-meter cylinder in one go.
No, not even close. You'd have to bring in overhead factory cranes just to unclamp the drum, then physically hoist it, rotate it, shift it down the line, and finally clamp it back down.
Which sounds like an invitation for disaster.
It is. Every single time you unclamp and reclamp a workpiece of that mass, you introduce cumulative positioning errors. The factory straps sit differently.
Right.
The sag profile changes slightly. The mechanical zero point is effectively lost.
Oh.
So over the span of 15 meters, a tiny fraction of a millimeter of drift at one end compounds into a massive structural misalignment at the other.
And then you have to add thermal expansion into that equation, too.
Oh, yes. The heat.
Right, because if factory floor temperature shifts by 10 degrees over the course of a 2-week manual drilling process.
Then the metal moves.
Exactly. That 15-meter steel structure physically expands and contracts. Your measurements from day 1 are physically no longer accurate by day 7.
It's a logistical nightmare. And the dedicated CNC drum drilling machine eliminates all of that through one defining mechanical philosophy.
Single clamping.
Yes, single clamping.
Meaning once the machine grabs the drum, it does not let go until the final hole is tapped.
Not once. The machine suspends the entire massive cylinder between a servo-driven rotary chuck on one end and a heavy-duty tailstock on the other to support all that weight.
Okay, so it's locked in place.
Right. And then the CNC system translates the CAD hole coordinates directly into servo indexing. When it's time to move to the next radial coordinate, the chuck rotates the drum to the exact microdegree required.
So the drum itself stays locked in a single fixed coordinate system for the entire production cycle.
Exactly. No cranes, no shifting sag profiles, no lost 0 points.
The productivity metrics in the sources are just wild. They note that depending on the configuration, you might have like 3 to 7 independent power heads working simultaneously.
It's an automated ballet.
It really is. You've got multiple drilling spindles moving axially down the length of the cylinder on heavy linear guideways, while that servo chuck indexes the drum to meet them.
Right. It takes a volatile 2-week operation and condenses it into a few days of synchronized automated machining. It boosts output by 3 to 5 times.
That is insane.
And you are standardizing the geometry, too. You completely remove the reliance on a single veteran operator's intuition.
Right. No more guessing if the punch mark is in the right spot.
Exactly. It eliminates all those compounding physical variables of manual handling.
So I am looking at the tooling schematics from the stack of sources you provided, and I'm genuinely hung up on something.
Oh, what's that?
Well, if the end goal is just to weld heating tubes or risers to a boiler drum, why does this machine need up to 7 different power heads?
I see where you're going with this.
I mean, it seems incredibly over-engineered if you just need to puncture the steel. Why all the different spindle configurations?
What's fascinating here is that in pressure-bearing equipment, a hole is never just an empty space.
Okay.
It is a highly engineered interface operating in an extreme environment. If you just punch a standard hole and stick a tube in it, well, that connection will fail catastrophically under superheated steam pressures.
So it's not just drilling.
No. The CNC machine is executing a series of specialized cuts to prep that interface.
Right, because the sources detailed the standard tube-through holes first, usually ranging from 20 to 63 millimeters in diameter.
Those are your primary fluid or steam channels. And under the right material conditions, the machine can plunge through holes up to about 52 millimeters in a single solid drilling pass.
Wow, that's a thick cut.
But the interface rarely stops there. You also have welding groove holes.
For the welds to grab onto.
Exactly. For high-pressure boiler tubes, a surface weld just isn't sufficient. The weld material needs to penetrate deeply into the joint to hold the pressure.
So it can't just sit on top.
Right. So the machine uses specialized combination tools to bore the hole and simultaneously cut a highly specific chamfer or slope around the entrance.
Okay, I get it. So it dictates the exact geometry of the weld pool before the welder ever even touches it.
Exactly. It does the prep work automatically.
And the schematics also show stepped encounter bored holes.
Yeah, those involve carving 2 or more different internal diameters within the same bore.
Why would you need that?
That geometry is crucial for housing internal sealing parts, or for creating flush assembly structures where a component needs to sit right beneath the surface profile of the drum.
Ah, okay. And then there's the reaming and tapping. I think reaming is one of the most critical mechanics here from what I read.
It's absolutely vital.
Because a heavy-duty drill bit chews through steel aggressively, which can leave, microscopic scoring and rough patches on the inner wall of the hole.
Right. Those microscopic scratches are known as stress risers.
Stress risers, right.
When you subject that steel to extreme atmospheric pressure, those tiny imperfections become the exact points where microfractures begin to form.
So the reaming fixes that.
Yes, reaming comes after the initial drill. A reamer is a specialized cutting tool that shaves off highly precise micro-layers of metal.
Leaving it smooth.
Exactly. It provides a glass-smooth internal surface finish and exact diameter control, which effectively neutralizes those potential stress risers.
And then tapping follows for any connections requiring internal threads.
Right.
But, and this is what blows my mind, if we are carving complex stepped grooves, pushing 63 millimeter bits through thick boilerplate and running multiple heads simultaneously.
The friction!
Yes, the friction has to be immense. The tool bit is buried inside solid steel for minutes at a time. How does the metallurgy of the cutting tool even survive without warping or shattering?
Well, heat is only half the problem. Chip evacuation is the real killer in deep hole drilling.
The chips.
Yeah, the displaced metal. If you are chewing through inches of solid steel, That metal has to go somewhere.
Right, it doesn't just disappear.
No, it doesn't. And if the metal chips pack tightly inside a deep bore, the tool binds. The torque spikes, and the bit just snaps off inside the wall of the drum.
Oh, geez.
Yeah, extracting a shattered tungsten carbide drill bit from a 15-meter pressure vessel is a costly, costly nightmare.
This is why the internal through-spindle coolant delivery system is so vital, isn't it?
Exactly.
Instead of just flooding the exterior of the workpiece with liquid, the CNC machine pumps high-pressure coolant directly down through microscopic channels inside the drill bit itself.
It's brilliant engineering. The coolant exits right at the cutting edge.
So it cools it from the inside out.
Right. It manages the thermal load precisely where the friction occurs. But more importantly, the high-pressure fluid acts as a hydraulic flush,
Blasting the chips out.
physically blasting the packed metal chips back up the flutes of the drill bit and out of the hole, keeping the entire bore clear.
And the machine control systems are actively monitoring that cutting environment too, right?
Oh, constantly.
Because it uses automated feed control to constantly read the torque and resistance on the spindle.
Yeah, it's essentially feeling its way through the metal.
If it hits an unusually hard spot in the steel alloy, it dynamically adjusts its feed rate to stabilize the cutting pressure.
It also features broken tool detection and automated tool retraction.
Okay, how does that work?
Well, if the torque spikes beyond a safe threshold, which indicates a potential bind, the system doesn't wait for human intervention.
It just pulls out.
It instantly retracts the spindle out of the bore to save the tool and protect the drum's structural integrity.
Which makes sense when you look at the margins they're working with. We're looking at adjacent hole pitch errors having to be within plus or minus 0.5 millimeters.
Practically nothing.
And the maximum long-distance positional error across the entire 15-meter surface is strictly kept within plus or minus 1.5 millimeters.
That's incredible.
To maintain that tolerance across a 50-foot span of curved steel while managing immense thermal friction, well, it's an incredible mechanical feat.
And if those tolerances slip, the downstream consequences are severe.
Like what? What actually happens?
Well, a positional error of a few millimeters means the massive prefabricated arrays of heating tubes simply won't align with the drum during final assembly.
It just won't fit.
Right. And if an angle is slightly off, or the welding chamfer is inconsistent, the joint requires forced fitting.
Oh, I see.
And forced fitting introduces latent mechanical stress into the joint before the boiler is even turned on.
And introduce superheated steam to a joint with latent mechanical stress. And you are inviting a rupture.
A catastrophic rupture.
This really brings into focus why these machines are the lifeblood of power generation, nuclear energy, shipbuilding, and petrochemical equipment.
And if we connect this to the bigger picture, this leads us to perhaps the most profound implication of utilizing a CNC drum drill in these specific industries.
Traceability.
Yes, exactly. The value goes far beyond the physical geometry of the hole.
Because of regulations.
Right. In high-pressure and nuclear applications, the regulatory bodies overseeing the manufacturing process demand more than just a finished pressure vessel. They demand a mathematically verified history of how that vessel was created.
Meaning the digital program isn't just a set of instructions. It serves as an immutable digital record.
Exactly. In heavy industry, the data trail is literally as important as the steel itself. When you use a CNC system, you generate validated acceptance data. You have a digital twin of the manufacturing process that proves exactly how, where, and to what strict tolerances every single interface on that drum was machined.
So if an inspector needs to verify the structural integrity of a nuclear containment vessel, say 20 years after it was manufactured.
They can pull the exact logs.
Right, they can pull the exact CNC operational logs. They know the feed rate, the spindle speed, and the precise indexing coordinates used for every single penetration in that steel.
You cannot achieve that level of rigorous compliance and traceability with manual center punching and radial drills.
No, of course not.
The CNC system functions as a liability and safety engine just as much as a manufacturing tool. It guarantees the absolute safety of that pressure vessel for its entire multi-decade life cycle by removing human guesswork from the equation entirely.
So, summarizing this deep dive into the sources you brought us, we've looked at the staggering limitations of traditional radial drilling, where cumulative positioning errors, thermal expansion, and gravity turn 15-meter cylinders into logistical nightmares.
Truly a nightmare.
And we explored how the shift to single clamping and servo indexing locked those massive drums into a flawless digital coordinate system.
Which is brilliant.
Yeah, and we broke down the mechanics of the complex cuts. From reaming away stress risers to hydraulic chip evacuation, all the things that ensure these immense pressure vessels can safely contain the volatile forces that power modern society.
I will say the sources do delineate one very clear boundary for this technology, which is important to note.
Oh, what's that?
The drum drilling machine is the ultimate specialist, meaning its architecture is entirely purpose-built for cylindrical parts.
Just cylinders.
Just cylinders. If a heavy industry manufacturer needs to drill a massive flat tube sheet for a different type of heat exchanger, this machine is useless to them.
They'd need something else.
Right. They rely on an entirely different ecosystem, like a specialized CNC plate drill. The servo chucks, the supporting tailstocks, the specific tool geometries, everything here is singularly dedicated to mastering the cylinder.
Which leaves me with a final provocative thought for you to explore beyond these sources.
Okay, let's hear it.
We've seen that digital programming, servo indexing, and single clamping are what it takes to tame conventional steel alloys for today's high-pressure applications.
Right.
But what happens as we push the boundaries of energy generation? What happens when our next-generation reactor vessels are constructed from advanced ultra-hard composites
Oh, wow.
or specialized metamaterials that cannot be penetrated by a spinning tungsten carbide bit without delaminating?
That's a huge problem.
If the materials that hold our future energy grids together defy conventional friction machining entirely, well, how will the machines that build the machines have to evolve next?
That is a great question. The structural demands of our energy infrastructure are always accelerating. The moment metallurgy takes a leap forward, the entire tooling industry has to reinvent its approach to geometry.
It's something to think about. Well, we want to thank you for bringing this fascinating stack of sources to the table.
It's been a great discussion.
It really is entirely too easy to overlook the microscopic tolerances required to build the most massive structures in our world. So, keep questioning the hidden mechanical systems surrounding you, because the machinery defining our industrial era is quietly operating with a level of precision we usually reserve for the microscopic scale.